Good morning, everyone. Today, we'll be doing a deep dive into how moving scheduling intelligence into the network fabric redefines cloud data center performance. I'll be presenting the paper titled Horus Granular in Network Task Scheduler for Cloud Data Center, which was featured in USENIX 2024. Let's begin by defining the core problem data center task scheduling bottlenecks. We are operating at a massive scale where cloud data center host huge number of short-lived and diverse tasks. Now, efficiently scheduling this task is absolutely critical. However, under heavy workload and suboptimal scheduling causes severe performance and pressure, leading to a high tail latency, resource waste, and severely degraded service quality. Traditional software schedulers are experiencing severe scaling pain because they were simply not designed for dynamism and sheer scale of the modern cloud native workload. This brings us to the core motivation the need for speed and scale. A cloud adoption accelerates globally. The volume of tasks and sheer number of workers are growing exponentially. Schedulers that once worked perfectly at the modest scale now become the very bottleneck they were meant to prevent, but they introduce unacceptable latency and waste of valuable resources. The key insight behind Horus is it brings scheduling intelligence closer to data, eliminating unnecessary round trips and enabling line rate scheduling decisions. Now, evolution of the data center task scheduling. To contextualize Horus, let's look at the okay. It was undergone a significant in transformation, moving from monolithic system to highly distributed network-aware solution to handle complex workload. Uh, First generation, the centralized. Early systems like Google, Borg, and Omega managed to everything from a single control plane. They were efficiently they were efficient for initial scale but become severe bottleneck as task diversity grew. And the second one, rack local. These systems like rack sets decentralized decision to individual racks. This reduce communication latency but struggle with the cross rack coordination and global pressure resource. Now, third generation network. This is where Horus sits. It embeds scheduling intelligence directly into the network fabric itself. This latest generation enables ultra low latency decision and optimal resource utilization. So exactly why do existing solutions fall apart? First, rack confined schedulers artificially limit parallelism because they can only schedule tasks within a single rack, leaving overall cross rack capacity untapped. Second, centralized scheduler act as a critical point of failure and a massive performance bottleneck as the data center scales up. And the third, task buffering at the center point adds unnecessary queuing latency and complicates state management. And finally, the, the state overhead of tracking every individual worker and task centrally become prohibited expensive, which degrades decision speed. So, what does Horus brings to the table to solve this? It introduces true in-network scheduling by distributing logic across switches for parallel line-rate task dispatch without needing a central coordinator. It utilizes a stateless design which minimizes per switch state and completely avoids uh, task buffering, keeping its memory footprint negligibly small. It features dynamic adaptation to handle the bursty and unpredictable nature of cloud workload through flexible virtual cluster configurations. And finally, it provides massive scalability, having been validated in simulations of up to 27,000 servers while completely outperforming state of the art alternatives. Let's explore the core concepts of the Horus architecture. Rather than central trackers, task requirements are encoded directly within the packet header as metadata, enabling intermediate in-network processing. Switches maintain minimum per switch state, only tracking empirical cluster metadata, which massively improves scalability. This relies on local decision logic, meaning each switch independently route task based strictly on its local state and conditions. Lastly, it leverages the fat tree multipath network topology inherent to modern data center to achieve fault tolerance and efficient load balancing. Uh, Now the implementation challenges. They faced strict programmable switches limitation as the ASIC memory of switch is incredibly constrained and not all switch support P4 programmability. They dealt with immense algorithmic complexity because encoding advanced scheduling logic into basic hardware is non-trivial. Debugging difficulty is so high, distributing decisions making across the entire network fabric makes troubleshooting much more complex, requiring careful integration to roll out gradually alongside legacy systems. Now, solutions and mitigations. To overcome these hurdles, the researchers implemented clear solutions. For hardware limits, we rely on hardware evolution, leveraging newer programmable switches with expanded memory capabilities like barefoot Tofino. We tackled complexity with simplified algorithms, designing hardware-friendly scheduling logic that fits efficiently within switch ASICs. We solved debugging with enhanced observability, developing robust telemetry and monitoring tools specifically designed for distributed in-network systems. And we approached deployment with hybrid deployment strategy, allowing for a gradual rollout with legacy schedulers to minimize disruptions. Now, how Horus works. At a high level, how does Horus actually work? Horus strictly separates fast path scheduling from slow path management. The data plane is responsible for the fast path, where switch hardware schedules traffic instantly at line rate. The control plane handles the slow path, managing reconfigurations and handling hardware failures. This architecture maps perfectly on a freight tree topology for efficient multipath routing, keeping the critical path lean while still recovering from failures. Now, performance benchmark. Let's look at the performance benchmark. Horus delivers truly unprecedented performance metrics. In testing across around 27,000 servers, Fat tree topologies, Horus generated 5 times higher throughput and 90% lower P99 tail latency compared to Rexed. If you look at the P99 latency figures, especially centralized schedulers, hovers around 1500 microseconds, and Rexed brought that down to 800 microseconds. But Horus drops the worst case latency to an astonishing 90 microseconds. And across P50, P95, and P99 percentiles, Horus outperforms older generation by orders of magnitude. Now, real-world applications. These performance gains empowers diverse demanding real-world applications. For latency-sensitive services like high-frequency trading and interactive applications, Horus provides crucial microsecond level scheduling. For bursty workload, it dynamically handles sudden spikes in task volumes while keeping the system responsive and better. And for machine learning training, it accelerates model development by tightly synchronizing and cooperating with large scale training jobs. Now, coming on to the strengths. It achieves high throughput and low latency by completely eliminating task buffering and parallelizing decisions at line rate. It demonstrates exceptionally scalability, actively outperforming leading alternative in large-scale scenarios, whether where it performs actually improve where its performance actually improves as the network grows. It significantly provides reduced overhead as distributing the intelligence removes costly communication rounds and state synchronization. Now, however, a critical analysis highlights important considerations. First is hardware logic complexity. Encoding these decisions directly into switch ASIC limits our algorithmic flexibility. Second is control plane reliability. While the data plane is distributed, we still heavily depend on the control plane for fault recovery. Third, we have strict hardware dependencies, meaning performance is tightly coupled to the capabilities of your underlying programmable switches. And finally, deployment friction. Moving away from legacy software schedulers demands a significant infrastructure and re engineering effort. And now, coming on to the future of data center scheduling. So ultimately, Horus represents the future of data center scheduling using in-network intelligence. It practically demonstrates that the network is no longer just a passive conduit of data, it is now a first-class participant in distributed computation. As programmable hardware continues to evolve, this model has the potential for massive, broad adoption across all cloud infrastructure. Now, this brings us to the end of the presentation. Thank you all for your time and attention.